Okay, let's jump into this. We've got some really interesting source material today. It's an article from Anthropic, and they're really digging into how they engineered a multi-agent AI system, specifically for research.
Yeah, that's the core topic. It's not just about one big AI, but how you get, multiple Claude agents to work together on tricky research problems. We're going deep into their process.
Right. And our mission here for this deep dive is to really pull out the key insights. What were the engineering hurdles? What lessons did they learn? What are the real benefits? And of course, the limitations.
Exactly. We want to unpack how breaking down these big, often fuzzy research tasks for different AIs, letting them specialize and collaborate, actually unlocks new capabilities. It's kind of like how human teams work, right?
Yeah, that coordination adds up to something more.
Precisely. Individuals coordinate, and suddenly the group can do vastly more.
So where do we start? What exactly is a multi-agent system in this context? And why is research such a good fit for this approach?
So basically, we're talking about multiple LLM agents, language model agents, that can autonomously use tools like web search in a loop. They interact, they work together toward some goal. Think of it as an AI team.
An AI research team.
And research is just, well, it's messy, isn't it? It's
Yeah.
open-ended, unpredictable. What you find now completely changes where you look next. That's path dependency.
Right, you can't just script it out step by
But
step.
a simple query,
Yeah.
a single shot, it just won't cut it. Agents need to run for a while, make decisions based on what they're finding along the way, autonomously.
It's more exploration than just lookup.
Totally. And a huge part of research is taking this massive amount of information and boiling it down, right? Compressing it into insights.
Mm-hmm.
Subagents are key here. They can work in parallel, each digging into a different aspect, each with its own temporary memory, its own context window. Then they summarize just the key stuff for the lead agent.
Ah, so they handled the info overload for the main agent, like
Yeah.
specialists briefing a project lead.
That's a perfect analogy. And it gives you this nice separation of concerns. Different tools, different prompts, different lines of inquiry all happening at once. It reduces that path dependency issue if one agent hits a wall.
The others might still find something useful elsewhere.
Exactly. Less chance of the whole thing getting stuck.
Okay, that makes sense. That's the foundation. Now, let's get to the exciting part. What are the actual tangible benefits? What did they see when they used this multi-agent approach?
Well, the source talks about this scaling principle. Once individual agents get smart enough, getting them to work together collectively scales performance way up dramatically.
So the synergy is real. It's more than the sum of its parts.
It seems so. Think about human societies. Our individual brains haven't changed that much recently, but our ability to coordinate, that's led to exponential progress. Same idea might apply here.
Interesting parallel.
And their own internal tests, their evaluations showed big performance gains, especially for breadth-first queries where you need to look wide and for pursuing multiple independent ideas at the same time.
Did they quantify that? Is there a number?
Oh, yeah. And it's pretty striking. They found their multi-agent system using Claude Opus 4 as the lead and Sonnet 4 for the subagents. It outperformed a single Claude Opus 4 agent by 90.2% on their research evaluation tasks.
90%. Wow. Okay, that's a huge difference.
It really is. It strongly suggests the architecture itself is providing a massive advantage.
Do they give an example? Like a specific task?
Yep. Identifying all the board members for every company in the S&P 500's IT sector. Big task.
Yeah, that's a lot of digging.
The multi-agent system broke it down, farmed out the work, got the answers. The single agent, trying to do it all step by step sequentially, it just got overwhelmed and failed.
Okay, that S&P example really drives home the power of breaking down the work. Parallel processing.
Exactly. And they looked into why this happens. Turns out, token usage, how much information is processed, explains about 80% of the performance difference in their browsing tests.
So it's partly just about being able to process more stuff simultaneously.
A big part, yeah. The multi-agent setup gets around the limits of a single agent's context window. It's like having several people at different desks with their own notes versus one person trying to juggle everything on one small desk.
Got it. Distributed context.
Right. They also mentioned that just upgrading the models themselves, say from Sonnet 3.7 to Sonnet 4, gives a bigger boost than just giving the older models more tokens to work with in a single agent setup. So better models plus the multi-agent structure is the winning combo.
Okay, those benefits are really compelling. But what's the catch? Where does this approach struggle? What are the trade-offs?
Yeah, there are definitely trade-offs. The big one, cost. These things are token hungry.
Ah, expensive to run.
Very. Their data showed like 15 times the token usage compared to a normal chat interaction.
Yeah.
and maybe 4 times more than a single agent using tools.
Okay, so you really need the task to be high value to justify that kind of resource burn.
Absolutely.
Hmm.
It's not for simple lookups, and it's not perfect for every complex task either.
Yeah.
Situations where all the agents need the exact same up-to-the-minute shared understanding of everything. That's tough currently.
Or where steps are super dependent on each other.
Right. Tasked with really tight dependencies, where Agent B immediately needs the output from Agent A's last action to even know what to do next. That kind of intricate real-time coordination is still hard for LLMs.
Can you give an example where that coupling is an issue?
Well, they mention coding tasks. Often, coding has fewer parts you can truly do in parallel without constant back and forth. The agents are great at dividing up research that can be done somewhat independently before synthesizing, less so at, like, pair programming line by line together.
Right. Good at splitting the research, not so good at collaborative writing in real time.
That's a good distinction. So where they really shine is on those high-value tasks that can be parallelized heavily, where the info needed is just too much for one context window and where you need to interact with lots of different, maybe complex tools.
Okay, that clarifies the sweet spot. So, knowing the pros and cons, let's peek under the hood. What's the architecture actually look like? How do they structure this AI team?
They went with a pretty standard pattern, actually.
What?
Orchestrator-worker. You have a lead agent, the orchestrator, who figures out the strategy and delegates tasks.
And the workers?
Those are the specialized subagents. They get assigned specific jobs by the lead and execute them, often in parallel.
Okay, walk us through it. Say I give it a research query. What happens?
Right. So your query comes in, the lead agent looks at it, analyzes it, figures out a high-level plan, how are we going to tackle this research, and crucially, it saves that plan to a dedicated memory component.
Why save the plan separately? Why not just keep it in context?
Because context windows are finite. As the research goes on, lots of tool calls, lots of results, older stuff, even the initial plan could get pushed out. Saving it ensures the lead agent doesn't, lose the plot midway through.
Prevents strategic drift.
Yeah.
Makes sense.
Exactly. So, plan saved. Then the lead agent spawns one or more subagents, gives each one a specific task from the plan.
Okay.
Each subagent then goes off and does its thing, maybe runs some web searches, maybe uses a different tool. As it gets results back from the tool, it uses something they call interleaved thinking.
Interleaved thinking. What's that? Like writing down its thought process?
Pretty much. It's like a scratch pad. The agent explicitly writes out, okay, I got these results. Are they good? Do they answer my sub-question? What's missing? What should I search for next? It helps them evaluate the information and plan their next move effectively.
So it thinks about the results before acting again.
Right. Once a subagent finishes its task or gathers enough info, it reports back its findings to the lead agent.
And the lead agent.
The lead synthesizes all the reports coming in, looks at the overall picture. Does the plan need changing? Do we need more research? Maybe spawn new subagents to dig into something unexpected that came up?
So it's this loop, delegate, execute, think, report, synthesize, replan.
Exactly. It keeps looping until the lead decides, okay, we've got enough to answer the user's original query, but there's one more step.
Oh.
Before sending the final answer back to you, all the gathered info and the source documents go to a dedicated citation agent. Its whole job is to meticulously go through everything and pinpoint exactly where each piece of information came from, generating proper citations.
Crucial for research. Ensures traceability.
Absolutely. So the final output you get is the synthesized answer with citations.
That's way more dynamic than, say, standard ORGAG, right? Which often just pulls static chunks.
Totally different. This is multi-step adaptive search and synthesis. It evolves based on what it finds.
It sounds like getting this complex dance choreographed correctly. Well, that must heavily depend on the instructions. Which brings us to prompt engineering. How did they figure out how to tell these agents how to work together effectively?
Oh, prompt engineering was massive. Absolutely critical. They said that as the system got more complex, the potential for errors just exploded. Agents doing weird things, spawning way too many subagents for a simple question, getting stuck, searching forever, getting distracted.
Yeah, I can imagine. Chaos potential seems high.
Right. So learning how to write the prompts to guide the lead agent and the subagents and how they interact, that was a huge part of the development.
So what did they learn? What are the key principles for prompting these kinds of systems?
They shared, I think, 8 key lessons. First one, think like your agents. You can't debug or improve prompts unless you can see what the agent is actually thinking step by step. They built tools to simulate and watch the agent's reasoning, which immediately showed problems like an agent just continuing to search even though it found the answer already, or using super long, clunky search queries.
You got to get inside their heads, metaphorically speaking.
Exactly. Second, teach the orchestrator effective delegation. This is big. The lead agent needs really clear instructions on how to break down the task and what to tell the subagents. Like, what's the goal? What format should the output be in? What tools should they use? What are boundaries?
Vague instructions lead to trouble.
Big trouble. Duplicated work, missed areas. They had an example about researching the semiconductor shortage where, without specific instructions to divide the work by year or topic, the agents just kept researching the same things.
Like a human team needing clear roles. Makes sense.
Totally. Third principle, scale effort to query complexity. Agents aren't inherently good at knowing if a question needs 5 minutes of work or 5 hours. So they built rules into the prompts. Simple fact. Okay, one agent, couple of tool calls, deep research question. Okay, spawn multiple agents, divide the labor clearly.
Built-in effort management. Smart.
Prevents wasting tons of resources on easy questions. Fourth, tool design and selection are critical. How the agent interacts with its tools matters immensely, and obviously it needs the right tools. If the info is only in Slack, giving it only a web search tool means it's doomed to fail.
Right. Tool for the job.
And how the tools are described to the agent is crucial too. Bad descriptions led to poor performance. They prompted agents to check the available tools first, match them to the task, and prefer specialized tools if available.
Okay. Tools are foundational. What else?
Fifth, and this one's really cool, let agents improve themselves. They actually found Claude 4 models could look at a prompt, be told about a failure, and then critique the prompt or the tool description and suggest improvements.
Whoa, really? The AI helps fix its own instructions.
Yeah, they even made a tool testing agent that could try using a tool, figure out why it wasn't working well because of a bad description, and then rewrite the description. And agents using the rewritten descriptions were significantly faster, like 40% faster task completion.
That's amazing. Meta learning for prompt engineering.
It's a powerful loop. Okay, sixth, start wide, then narrow down. Like human experts, right? Don't start with a super specific search query that might yield nothing. Prompt the agents to begin broader, get the lay of the land, look at the results, then focus the search more narrowly.
Explore first, then drill down. Good heuristic.
Seventh, guide the thinking process. That interleave thinking scratchpad we talked about. Making agents use it explicitly was key. The lead uses it to plan the whole approach. Subagents use it after getting tool results to evaluate quality, spot gaps, and plan their next specific action. It improved reasoning, instruction following, the works.
Making the thought process visible and structured helps them stay on track.
Definitely. And eighth, this was a game changer for speed. Parallel tool calling. Early versions had agents making tool calls one after another. Super slow.
Yeah, bottleneck.
Huge bottleneck. So they enabled parallelization. The lead can spawn subagents that work in parallel, and those subagents can make multiple tool calls in parallel if the tool itself supports it. This cut research time for complex stuff by up to 90%.
90. Wow, okay. Parallel everything drastically speeds it up. So summing up the prompting strategy, it sounds less like rigid rules and more like instilling good habits, good research heuristics.
That's exactly it. Teach them strategies like decomposition, quality evaluation, adapting the approach, managing effort like you'd teach a human researcher, plus proactive guardrails, fast testing, and good ways to observe what's happening.
Okay, so we've got the architecture, the prompting strategies, but how do you know if it's working? Evaluating something this dynamic where agents can take different paths to the right answer sounds really challenging.
It is challenging. You hit the nail on the head. You can't just check if it followed script A. Lots of paths might be valid. So you have to evaluate the outcome. Did it answer the question well? And also, was the process it followed reasonable, efficient, sensible?
Focus on the result and the journey's reasonableness, not just the exact steps. How did they approach that?
They used a few methods. First, start small and evaluate early. Don't wait for some huge, perfect evaluation data set, especially at the beginning. Test with like 20 queries that represent typical use. Small changes can have big impacts, so you want to see those immediately. Fast feedback loops.
Don't let perfect be the enemy of good, especially early on.
Exactly. Second, LLM as judge. Since the output is often free-form text, using another powerful LLM to grade it makes a lot of sense. They developed a single, detailed judge prompt with a rubric covering everything.
Wow.
Factual accuracy, citation accuracy, completeness, source quality, even tool efficiency. Asking for scores and a pass-fail worked best and scaled well.
Using AI to grade AI seems efficient.
It is, for handling volume. But, and this is crucial third, human evaluation is still essential. Automation misses things. Humans caught edge cases, subtle hallucinations on weird queries, system failures the LLM judge didn't notice, and, importantly, biases.
Biases? Like what?
Yeah, humans noticed the agents were sometimes preferring, like, SEO spam sites over actual authoritative sources just because the spam ranked higher in search results.
Oh, wow. That's subtle but important.
Totally. That feedback led directly to adding prompts specifically about prioritizing source quality. It just highlights that you absolutely need humans in the loop for evaluation, especially for catching these nuanced issues.
Automation helps scale, but humans catch the tricky stuff. Got it.
And this all ties into emergent behaviors. You tweak one small thing in a prompt, and suddenly the subagents start interacting in a completely different, unexpected way. So prompts aren't just instructions, they're like frameworks for collaboration, defining roles, how problems get solved, effort budgets. You have to understand those interaction patterns.
Right, it's a system dynamic you're tuning. Okay, so we've designed it, prompted it, evaluated it. Now the final hurdle, taking this from a working concept in the lab to a reliable production system that real users depend on. What were the big engineering challenges there?
This was a big focus in the source. The core difficulty is that these agent systems are stateful, they remember things over long interactions, and because of that, errors compound really badly.
Meaning a small glitch early on can totally derail things later.
Precisely. It's not like stateless web requests where each one is independent. Here, one bad step, one failed tool call, can send the agent down a completely wrong path because its internal understanding, or state, is now flawed. They said the gap between a working prototype and a truly reliable production system was much wider than they initially expected.
That makes sense. So how do you handle that statefulness and error compounding?
You need durable execution and really robust error handling. Users get frustrated if a long research job just fails and they have to start over. So you need ways to not just detect errors, but ideally resume the agent's work. Interestingly, they found that sometimes just telling the agent, hey, that tool failed, and letting the agent itself try to adapt its plan worked surprisingly well.
Huh. Let the AI try to fix the problem.
Yeah, leverage its adaptability. Combine that with more deterministic safeguards like automatic retries for tools, saving checkpoints, things like that. Another huge challenge. Debugging.
I bet. If it's non-deterministic, how do you even find the root cause when it messes up?
Exactly. Why did it fail to find that obvious piece of information? Was it a bad search? Bad evaluation of the results? Tool hiccup? Misunderstood prompts? It's tough. They needed really good production tracing, monitoring the patterns of decisions, the structure of agent interactions, without looking at the user's private data, of course, to diagnose these things.
Visibility into the process, not the content.
Right. Deployment is also tricky. These aren't just static models. They're systems with prompts, tools, logic, all running continuously and holding state. Updating them without breaking ongoing user sessions requires care. They use things like rainbow deployments, gradually shifting traffic to the new version while keeping the old one running for a while.
Smooth transitions are key.
Definitely. And they mentioned one current limitation in their architecture: synchronous execution. Right now, the lead agent basically has to wait for all the subagents it spawned for a particular step to finish before it can process their results and decide what's next.
Ah, so it creates bottlenecks. The whole system waits for the slowest subtask.
Exactly. The lead can't jump in and redirect a subagent that's going off track. The subagents can't easily coordinate directly with each other. And yeah, everything waits. It simplifies coordination logic, but hurts parallelism.
Like a manager who can only check in when everyone has finished their assigned piece.
Good analogy. The future probably lies in asynchronous execution, letting everything run more independently. That adds a ton of complexity. Coordinating results arriving at different times, keeping state consistent, handling errors that pop up concurrently. But the potential performance gains are likely worth the engineering effort down the line.
Okay, so after wrestling with all these complex engineering, design, prompting, evaluation challenges, what's the payoff? Are these systems actually making a difference? Are people finding them valuable?
According to the source, yes, definitely. They've proven genuinely valuable for these kinds of complex, open-ended research tasks we've been talking about.
What are some examples? What are people actually using them for?
They shared some user feedback. Things like finding new business opportunities, helping navigate complex topics like healthcare regulations, sorting out tricky technical bugs. One quote mentions saving days of work because the system could quickly surface connections and research that would have taken a human ages to find manually.
Saving days of work, that's a serious impact.
Yeah, it really speaks to the power of synthesizing information quickly. The source listed the top categories people reported using it for. Things related to software systems, about 10% of uses, drafting professional or technical content, 8%, developing business strategies, also 8%, helping with academic research or educational materials, 7%, and researching or verifying info about people or organizations, 5%.
So it sounds like it's really hitting its stride in any area that involves digging through a lot of information, connecting dots, and synthesizing findings.
That seems to be the core value proposition,
Yeah.
yes.
Okay, so let's zoom back out then. We've taken this deep dive, and we've seen that building these multi-agent systems, well, it's not simple. It requires serious engineering, learning from mistakes, really careful design thinking around prompts, tools, how you evaluate it, and tackling these tricky production issues like state and coordination.
Definitely complex, but the big takeaway, despite that complexity, is that these systems are already showing incredible value. They're tackling problems, those complex, open-ended research questions that single agents or just traditional computing methods really struggle with. It feels like a significant shift in how AI can approach information gathering and synthesis.
A new way to scale AI's capabilities, really.
It really seems like it.
And maybe here's a final thought for you, our listeners, to chew on, drawing just from what Anthropic shared in their work. They really emphasize that going from a cool prototype to a production-grade multi-agent system is a big leap, needing robust engineering and careful orchestration. But that core idea they proved works coordinating specialized AI agents achieves more than individuals that strongly mirrors how human societies gained power through specialization and collective intelligence. So thinking about that principle, what complex problems or areas of curiosity in your own work or just your own life could perhaps be tackled more effectively if you started thinking about breaking them down, breaking them into specialized tasks for coordinated agents, even if those agents are just different approaches or tools you use yourself?